This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we're delving into a paper titled Understanding Silent Data Corruption in LLM Training. This research explores a critical, often overlooked problem in the training of large language models, LLMs, silent data corruption, SDC. What are the key challenges posed by SDC in LLM training, and why is this paper significant?
The core challenge with SDC is its insidious nature. Hardware malfunctions can produce incorrect computations without triggering any error signals. This means training proceeds silently, but with flawed data, potentially leading to subtle or catastrophic model degradation. The significance of this paper lies in its empirical investigation using real-world data from production nodes experiencing SDC. Most previous work relied on simulations, which may not fully capture the complexities of real-world hardware failures.
The paper mentions that the impact of SDC varies across different nodes. Can you elaborate on the different levels of analysis employed in the study to understand this variability?
The researchers analyze SDC's impact at 3 granularities. 1. Submodule computation, examining the accuracy of individual transformer components like self-attention and feed-forward networks. 2. Single optimizer step, analyzing the effect on gradients during a single optimization iteration. 3. Training period, assessing the cumulative impact on model quality over the entire training process. This multi-level approach provides a comprehensive understanding of how SDC propagates and affects the final model.
The paper uses synchronization mechanisms to isolate the impact of SDC. Can you explain the computation synchronization and parameter synchronization techniques used and why they are crucial for accurate analysis?
Computation synchronization ensures that the input to each submodule is identical on both healthy and unhealthy nodes. This is achieved by overwriting the unhealthy node's intermediate results with those from the healthy node. Parameter synchronization, on the other hand, ensures that model weights are identical at the start of each optimizer step, preventing error accumulation across iterations. These techniques are crucial because they allow the researchers to isolate the impact of SDC from other sources of variation, such as numerical instability.
The paper presents results showing that SDC doesn't occur uniformly during training. What are the key findings regarding the frequency and severity of SDC at the submodule level?
The results reveal significant variability in SDC occurrence across different nodes. Some nodes showed a high frequency of errors, while others exhibited almost no errors. Even within a single node, the frequency of errors varied over time, often appearing as spikes. Regarding severity, while the average mismatch frequency was generally low, SDCs could cause individual tensor values to differ by large factors, sometimes exceeding 100 times the correct value.
How did SDC affect gradients at the single optimizer step level, and what was the overall impact on model quality over the training period?
At the single optimizer step level, the noise introduced by SDC in gradients was relatively small compared to the norm of the true gradients. However, over the entire training period, SDCs caused model parameters to drift away from the ground truth, indicating convergence to different optimists. While pre-training loss remained similar, fine-tuning revealed a more significant impact, with some nodes experiencing loss spikes that could severely corrupt the model's performance.
The paper discusses the silent nature of SDCs and explores potential mitigation strategies. What are the key takeaways from this discussion, and what are some promising avenues for future research?
The silent nature of SDCs highlights the need for robust detection mechanisms. The paper explores the limitations of algorithm-based fault tolerance, ABFT, in detecting these errors, suggesting that more sophisticated techniques, such as shadow replicas, might be necessary. Future research should focus on improving SDC detection, mitigating the impact of undetected errors, perhaps by addressing the sharpness of the loss landscape, and developing more effective recovery strategies.
The paper acknowledges limitations such as the limited number of unhealthy nodes available for the study. How do these limitations affect the generalizability of the findings, and what are the implications for future research in this area?
The limited number of unhealthy nodes restricts the statistical power of the study and might limit the generalizability of the findings to other hardware configurations or training setups. Future research should aim to expand the dataset of unhealthy nodes to improve the robustness of the conclusions. Furthermore, investigating the impact of SDC in larger-scale, multi-node training scenarios is crucial for understanding its effects in real-world LLM deployments.
This paper highlights a trade-off between fine-grained analysis and SDC occurrence. Can you elaborate on this trade-off and its implications for experimental design?
The synchronization mechanisms used in the study, while crucial for isolating SDC's impact, introduce overhead and reduce accelerator utilization. This, in turn, can decrease the frequency of SDC events, potentially underestimating their true impact in real-world scenarios. Future research should explore more efficient synchronization techniques or alternative experimental designs that minimize this trade-off.
The discrepancy between the occurrence of loss spikes in fine-tuning versus pre-training experiments is noted. What are the potential reasons for this discrepancy, and how might it inform future research?
The lack of loss spikes in the pre-training experiments might be due to the limited number of training steps or the relatively smaller model size used. Loss spikes are more likely to occur in longer training runs with larger models. Future work should investigate this further by conducting longer pre-training experiments with larger models on unhealthy nodes, potentially in a multi-node setting, to better understand the relationship between loss spikes, NANs, and SDC.
In summary, what are the most important contributions of this paper to the field of LLM training and reliability?
This paper is the first to provide a detailed empirical analysis of real-world SDC's impact on LLM training using data from production nodes. It offers a multi-level analysis framework, reveals the non-uniform and potentially catastrophic nature of SDC, and highlights the limitations of existing fault tolerance techniques. The findings provide valuable insights for improving SDC detection, mitigation, and recovery strategies, paving the way for more robust and reliable LLM training systems.
Thank you for this insightful discussion. This has been a very informative exploration of a critical issue in LLM training.